Uh, Clausius statement of second law of thermodynamics. So Clausius' statement from the second law of thermodynamics states that it is impossible to design a device which runs on a cycle and has the sole purpose of heat transferred from such a cooler to a warmer object. Note that heat doesn't move on its own from something to cold or something to hot, from something cold to something hot, unless energy is used up to make it happen. This is how fridges and heat pump works. A fridge moves heat from the inside, where it's cold, to the outside, where it's warmer, but it needs electricity to do this, which power its motor. So naturally, heat naturally flows from a hotter body to a cooler body. The Clausius statement tells us that reverse process, heat flowing from a colder body to a hotter body, cannot occur spontaneously unless there is work done. Um, Clausius states that the algebraic sum of each and transformations occurring during a cycle process must be lower than zero, as well as the inside extreme case, equatable to nothing. Oh, and this is the Clausius statement illustration. See, this is the high temperature, and this is the heat engine. This is the yeah, you get it, you get it. So yeah, in the regard this one, regard the part where this one. High temperature reservoir source at T1 temperature. Oh, heat engine. Q1, Q2 low temperature. So the high temperature is located at the top, and the low temperature is located at the bottom, where between them is the heat engine. Heat engine, and inside and on the process is the work done as well. So continue with the integral, maybe integral. So the with representing energy flow into system due to heating, and T representing the absolute temperature of the body whenever that the energy is absorbed. So as you can see here in the statement proof, this is just a proof of the rule or law, or rather the equation. The system is represented by the gas in the piston in the diagram. To add heat, which is Q sys or Q system, to the framework at a local various temperature T. Researchers were using a Carnot heat engine pump. Work sys system is performed on the system during the process. Q sys and W sys can both be positive or negative. The Carnot engine's cold reservoir is at T initial. The Kelvin Planck states that the Kelvin Planck statement of the second law says that it's impossible to get net work from a system after completing a full cycle. Looking at the diagram, this means that the total work done by the Carnot and engine system together, W Carnot and W sys, must follow this rule. Due to energy conservation, and since both the system and the engine return to their starting states, any net work done must correspond to heat being added to the reservoir. This means that Q reservoir is greater than zero. Looking at the Carnot engine now, we can see that if we add heat at some point during the cycle, thus we get the dQ of the reservoir equals to the T initial over T, and the dQ of the system. And T initial represents the temperature of the reservoir, and T is the temperature at which heat is transferred, and dQ of the system refers to the infinitesimal heat transfer within the system. So this part introduces the Carnot engine, showing that when heat is added at some point during the cycle. Now we have this because the heat extracted is lower than zero. This is the third part. So third part. The final part connects the heat transfer to entropy changes using an integral form. This is a mathematical way of saying that for a reversible process, the energy entropy change is zero or less than zero, or less. Here, The integral denotes the clinic integral, sum of changes over one complete cycle, in the equality of greater or less than zero, less than or equal to zero, comes from the second law of thermodynamics, entropy, which entropy cannot decrease in a natural process. If the system operates in a reversible cycle, all quantities will be simply reverse their signs. However, if Q reservoir started as less than zero, it would become positive in the reversed way, or the reverse cycle, leading to a network being extracted and violating the Kelvin-Planck statement. Therefore, in a reversible system, Q reservoir must be exactly zero, as you can see.